Thanks for having me. My name is Jenna Brown, and I work under Dan Zimmerly at the CSU Energy Institute. I'm currently studying to get my master's in mechanical engineering. So I'm going to be talking about how measurements can inform inventories. So what brings us here today, obviously, is methane emissions. And there's obviously been an increased emphasis on reducing those emissions from oil and gas. And there's been a lot of regulatory news in the EU, U.S.A, and Japan. So typically what we've had is that facilities had to report their methane emissions, and that was typically using greenhouse gas reporting program. But more recently, we have these technologies like we had someone from CCOPS talk. So we have these new technologies that can come out and measure on-site emissions. So like I said, we have the government required inventory, but that has a lot of loopholes in it. And we've been going more towards an enhanced inventory. And then we have these top-down estimates come out and measure methane emissions from the top down. But like we're seeing this disagreement between the top down, bottom up. So in an ideal world, we would have this continuous monitoring of whole facility measurements. But from where we're at right now, that's a big jump. From the continuous monitors aren't quite there yet. And these top-down estimates are just a snapshot of emissions. So how do we use these measurements to inform the inventories? We're kind of in this intermediate phase, and we're not quite to the continuous monitoring. So how do we use these snapshot measurements? So this measurement-informed inventory concept, first you have to keep the inventory up to date using best methods such as greenhouse gas reporting. You have to track operational data, find and fix any fugitive emissions. Periodically, you would have a full facility estimate. So a top-down come out, measure your methane emissions. You do that so many times a year. And hopefully the results from these top-down estimates would be able to help you find gaps in your inventory so that the inventory over time becomes more defensible and more correct. So how do we use these measurements to inform the inventories? That's a grand question, right? So these programs on the right are starting to require some empirical data in their inventory. But an inventory is a year-long annual inventory, and these surveys are seconds to minutes long. And while these programs are very vague on how to actually do this, how do we adjust for the changes from the snapshot measurement to an annual period? So that's sort of the motivation behind this QMRV project. So the QMRV stands for Quantification, Monitoring, Results, and Verification. And I believe Will and Lyra presented on the production side of this study. So I'm presenting on the midstream side. So this was funded by Cheniere, and the goal was to reduce emissions across the supply chain. They also wanted to try to verify the accuracy of the reported emissions and improve emission transparency. So our role in this study was to develop measurement-informed inventory methods using multi-scale measurements. In this study, we had 6 different midstream companies and 15 facilities enrolled. So the program was designed like this. We had a baseline period, and that's mostly what I'll be focusing on today. We had an enhanced monitoring period, which was 6 months long, and the end of project. So in the baseline period, operators were required to estimate an inventory, again, using the bottom-up methodology. And I'll touch on this a little bit more later. We had 2 top-down methods come out and measure the facility emissions. And then we were supposed to come up with a measurement-informed inventory and compare that to the operator estimated inventory. The enhanced monitoring, we asked operators to do a monthly OGI or LDAR survey or have continuous monitors. And then the end of project is after the 6 months. We had the operators estimate another inventory. And again, the top-down methods come out. So we're trying to see some sort of trend in what we're seeing. But today I'll just be focusing on the results from the baseline phase. So when I say that the operator estimated an inventory, I just wanted to bring up this slide to highlight that they are we're shrinking this annual inventory to just 1 day and making so that it's comparable to these snapshot surveys that we're having. So the operator estimated inventory, we provided some companies, we provided all the companies a guidance document, and for each emission source, we compared the greenhouse gas reporting methodology versus an improved method, which typically involves some sort of measurement. We also asked operators to estimate episodic events such as blowdowns or any upset conditions on the facility during that day. So what that looked like was this table down here below. You'll see is what an operator gave us. And you can see that compressor driver combustion is the largest source of methane, and that's pretty typical at these midstream facilities that have a lot of compressors at the station. And while we gave this guidance document to all the companies, each company reported a slightly different inventory. Some were a little bit more passionate about this project than others. So the two top-down measurement methods that were contracted were Bridger Photonics gas mapping LiDAR. So this is a airplane, and they have a laser system that sweeps perpendicularly across the facility. They use differential absorption to compute path integrated methane concentration, and they utilize wind data to compute an emission rate. We also had CCOPS, which is a flex plane mass balance drone. They had a tunable laser spectroscopy sensor mounted on a drone, and they measure methane concentration by flying downwind passes through the facility emissions at different heights. They also use wind data to compute an emission rate, and CCOPS typically measures subsets of equipment at the facility. So how do we align these top-down estimates to the OEI to be on the same temporal basis and account for the differences in detected emitters? So the main issue in aligning these two was that the operating states changed a lot in these midstream facilities. So when I say operating state, that means like, say a facility has 5 compressors, they can cycle through having 1 compressor on to 5 throughout the day. So say Bridger flew over, there were 4 compressors operating, and then CCOPS measured, and there was one. So those aren't 2 comparable estimates. So we asked the operators to provide an OEI so that individual operating states could be extracted. Typically that included providing us with a pressure log of these compressors. We also had an on-site observer out there for each day of measurement, and they noted the timing of any compressor state changes and any episodic events. This allowed us to remove the episodic event from the top-down estimates, because these top-down estimates can't reliably estimate total emissions from an episodic event. So once we do this, the top-down estimates can be compared to the OEI in the same compressor operating state. So this is a little bit of background on the facilities that we had enrolled in the program. So we had some facilities in the transmission and storage sector and others in the gas and processing. We had compressors that were either recip or turbines, and there was anywhere from 1 to 15 compressors at these facilities. So some of the trends we saw, like I said, Bridger is able to detect specific emitters. and CCOPS slides those downwind subsets. And so Bridger has a minimum detection limit. So we had to add things onto Bridger that were, say, below that minimum detection limit, or things that they missed. So in this case, on-site detections is emissions from pneumatics, which are too short to be detected by this quick flyover. We also added in like other exhaust, which is combustion emissions from flares and heaters. So once we did that, the trends that we typically saw was that Bridger was higher than, or CCOPS was higher than Bridger, and both these top-down methods are larger than the OEI. So some other issues that we ran into were obviously the compressor state changes. These midstream facilities are complex and they added some unique challenges. Again, Bridger had a minimum detection limit, so we had to add in anything that was below that. And we found that there's sometimes capturing exhaust, sometimes it's not totally clear what the exact source is. And the grand question that we're trying to figure out is, why is CCOP so much greater than Bridger plus these corrections that we made? So this table shows the aggregate emissions over the 15 facilities. So when I say that Bridger is maybe capturing exhaust, this is an example here on the left side. We can see clear plumes coming from these exhaust stacks on the south side of the building. And then on the right, the exhaust stacks are again on the south side, but it's unclear where this plume is coming from. It seems like the wind field and the compressor building are causing some unique challenges here, like I said. And this is important because methane slip can account for more than 50% of a facility's emissions at these midstream sites. So for our uncertainty analysis, we use controlled release testing. During controlled release, there's a known source, a known emission rate, which is the release, and we compare that to an unknown estimate from the method. So say the controlled release was 1 kilogram per hour, and Bridger gives us an estimate of 0.5 kilograms per hour. Now we have the opposite case where Bridger gave us 0.5 kilograms per hour. We're trying to estimate what the actual emission rate is. So we come up with this relative error model and we apply that to each estimate. And we use Monte Carlo methods to propagate uncertainty. So here's an example of that in this table. And you can see that the increase in the mean here just shows that there's some bias in the controlled testing environment. So the first thing we wanted to do was compare these top-down estimates. So we had two popular aerial methods come out on the same day under the same conditions at the same facility. And yet over the 15 facilities in the mean, we're seeing a difference of 31%. And on a per facility basis, we're seeing anywhere from 10 to 15% difference. So this plot on the right here is a Bland-Altman difference plot. So the y-axis is showing the difference between Bridger and CCOPS normalized by the MEC. And the MEC is just the average of Bridger and CCOPS. So this is important because, well, there's a lot of regulation that's requiring methane fees coming up. If you were to choose Bridger to come out or CCOPS, the difference between what you're paying could be $10 million, for example, and that's a lot of money. So how do we use these measurements to inform the inventory? So based on the daily operator estimated inventory, which again was that small box that I highlighted here, compared to these snapshot surveys, we have a disagreement on that one day. So what can we learn from that one day and apply that to an annual period and make that be more representative of the emissions at the facility? So next we looked at comparing the top-down estimates to the OEI. So on the top we have the difference between the OEI and Bridger, again normalized by the MEC, and on the bottom the difference between the OEI and CGOPS. So over the 15 facilities, the top-down estimates are anywhere from 68 to 99% larger than the operator inventory. And only at 2 of the 15 facilities was there a close match for one of the top-down methods. So here's a list of some of the inventory issues that we ran into. I'm going to give an example. So we had an operator submit their inventory, and then they looked at it and realized that they missed estimating the crankcase vents. We had another operator that didn't estimate rod packing emissions. And so while those are substantial sources at these midstream facilities, it may only increase inventory a few kilograms per hour to, say, in an extreme case, maybe 10 kilograms per hour. So how do we explain the top-down, bottom-up disagreement? So we haven't found an explanation with having an on-site observer there and a ground team that would A, miss tens of kilograms per hour of emissions, and B, that emission source not be visible to Bridger. So while these top-down estimates are a good check of emissions, it requires some on-site work to understand what's happening and why this gap still persists in all these studies that we're seeing, right? So some of the reasons for the gap, again, like I just said, bottom-up inventories may be systematically underestimating sources. There could have been an uninventoried source that existed at the facilities, although this is pretty rare. And the top-down methods could be biased high because they have not been extensively tested at these complex facilities. So while these are all possible cases, we have little evidence in supporting them. So we made some adjustments during the end of project measurements to hopefully answer those questions. So we had CGOPS fly down just one pass downwind of the facility to get a whole facility estimate. We wanted them to get as many as they could to treat these as independent measurements. We also had Bridger fly over throughout the whole day and trying to get the most independent measurements possible. We also had 2 facilities that were doing additional diagnostics. So what that looked like was same-day stack testing. They had someone come out and measure crankcase vents, and they also had an OGI and high flow team out there. So the goal of these adjustments was to increase the number of whole site measurements to account for the changes in the operational configurations, and again, see if more measurements will decrease the uncertainty in the top-down methods. And with that, I'll open it up to any questions. Thanks for having me.